In 1965, Perkins launched the V8.510, a diesel engine so advanced it was set to crush American competition. It had power, torque, and tech, years ahead of its time, but it disappeared out of nowhere, banned by operators worldwide. But why would an engine so ahead of its time be banned so disgracefully? Let's uncover the hidden flaws that doomed the Perkins V8.510. It's 1965, and British engineering is riding the crest of a golden wave. The Mini Cooper is conquering rally stages across Europe. Jaguar's D-Type has just claimed victory at Le Mans for the third consecutive year, and the entire world is looking to Britain for automotive innovation. Against this backdrop of triumph, Perkins Engines, the Peterborough-based company that had powered everything from humble tractors to Royal Navy destroyers, was preparing to unleash their most ambitious project yet.
Should be. Well, I love it. I do. Absolutely love it.
The V8.510 wasn't conceived as just another diesel engine. This was Perkins's declaration of war against American diesel dominance, a precision-engineered masterpiece designed to prove that British ingenuity could match anything Detroit had to offer. The project had consumed 4 years of development, involved their best engineers, and represented the largest single investment in the company's 40-year history. When the covers came off at the 1965 Commercial Motor Show in London, industry veterans were genuinely stunned. Here was a diesel V8 that looked more like a racing engine than a commercial power plant. The deep red paint gleamed under the exhibition lights, and every surface spoke of meticulous engineering attention. The specifications told an equally compelling story. This 8.36-liter V8 delivered 170 brake horsepower at 2,800 RPM, but the real headline was the torque figure. A massive 380 pound-feet available at just 1,500 RPM. To put that in perspective, contemporary American V8 diesels of similar displacement were producing perhaps 320 pound-feet, and they needed higher RPM to deliver it. The Perkins engine was offering 20% more torque where it mattered most for commercial applications. The engineering team, led by Chief Designer Harold Whitworth, had made deliberate choices to optimize for real-world commercial use. The undersquare design, with its 4.25-inch bore and 4.5-inch stroke, was specifically calculated to maximize low-end torque production. While over-square designs were becoming fashionable for high RPM applications, Whitworth understood that commercial vehicles needed pulling power, not peak horsepower figures. The construction philosophy was equally thoughtful. Instead of following the wet liner approach common in British diesels, Perkins opted for dry liners made from high-duty cast iron. This decision wasn't made lightly. Dry liners offered superior rigidity, better heat transfer, and the possibility of individual cylinder replacement without major engine disassembly. For fleet operators managing hundreds of vehicles, this maintenance advantage could translate to thousands of pounds in reduced downtime costs. But the real innovation lay in the fuel system. While most diesel manufacturers were still using indirect injection, with its inherent efficiency losses and complexity, Perkins boldly committed to direct injection technology. This was genuinely cutting-edge stuff in 1965. Each cylinder received fuel through a centrally mounted injector positioned directly above the piston crown. The injector featured a 4-hole, pintle-centered design that created an optimized spray pattern for complete fuel atomization. The direct injection system promised multiple advantages. Fuel economy would improve by approximately 15% compared to indirect systems. Cold starting would be more reliable. Power output would be higher for a given displacement. Most importantly, for commercial operators, the engine would run on lower-grade fuel without the knock sensitivity that plagued gasoline engines.
You all right?
Physical packaging had been another major consideration. At just 36 inches long, 33 inches wide, and 32.5 inches tall, this V8 was remarkably compact for its power output. The 90-degree V angle provided excellent primary balance while keeping the engine narrow enough to fit within existing truck and bus chassis designs. At 1,238 pounds bare weight, it was actually lighter than many inline-six diesels of equivalent power. The cooling system incorporated advanced features that seemed to address every potential weakness. A high-capacity centrifugal pump circulated coolant through carefully designed passages that promised even temperature distribution across all 8 cylinders. The radiator mounting system accommodated the increased heat rejection while maintaining the compact installation envelope that made the engine so attractive to vehicle manufacturers. Lubrication followed proven Perkins principles, but scaled up for the increased power and complexity. A gear-driven oil pump provided reliable pressure feed to all critical bearing surfaces, while a sophisticated splash system handled cylinder wall lubrication and piston cooling. The full-flow filtration system ensured that contamination wouldn't compromise the precision-machined bearing surfaces. Early demonstrations were nothing short of spectacular. Perkins arranged for journalists and potential customers to witness dyno runs where the V8.510 would pull cleanly from 800 RPM to its 3,200 RPM redline without a hint of roughness. The sound was intoxicating, a deep, purposeful rumble that spoke of controlled power. Unlike the agricultural clatter of typical diesels, this engine sounded refined, almost civilized. The marketing department at Perkins was beside themselves with excitement. Here was a British engine that could compete directly with anything from Caterpillar, Cummins, or Detroit Diesel. The power-to-weight ratio was competitive with the best American offerings, while fuel economy figures promised to be substantially better. Orders began flooding in from across the Commonwealth, with particularly strong interest from Australia's booming mining sector and Canada's long-haul trucking industry. Bus manufacturers were equally enthusiastic. The smooth power delivery and compact dimensions made the V8.510 ideal for urban transit applications where passenger comfort and tight packaging were paramount. Several major British bus builders, including Leyland and AEC, began developing chassis specifically designed around the new Perkins V8. Generator manufacturers saw enormous potential in stationary applications. The combination of high power output and compact dimensions meant that emergency generators could be significantly smaller and lighter while delivering the same electrical capacity. Hospitals, data centers, and critical infrastructure facilities began specifying V8.510 powered generators for their backup systems. Even military applications seemed promising. The Royal Army Service Corps expressed interest in truck applications, while the Royal Navy was investigating the engine for auxiliary power systems. The compact dimensions and robust construction made it attractive for mobile equipment where space and weight were critical constraints. But then, reality struck with devastating force. The first warning signs appeared within just 3 months of the engine entering commercial service. Fleet mechanics at a major Birmingham bus company began reporting unusual vibration patterns that seemed to have no correlation with standard V8 harmonic characteristics. Unlike the smooth power delivery that had been demonstrated during the launch events, operators were discovering unsettling resonances that became particularly pronounced during part-load operation or when running outside the narrow optimal RPM band. These weren't the typical diesel vibrations that mechanics had learned to expect and accommodate. The V8.510's vibrations seemed to follow no predictable pattern, sometimes smooth as silk at idle, then suddenly developing a harsh buzz under light acceleration that would mysteriously disappear at higher loads. Drivers complained of steering wheel shake that made long-distance driving exhausting, while passengers on buses powered by the V8.510 began specifically requesting alternative routes. The engine's sophisticated direct injection system, which had been marketed as its greatest technological achievement, quickly became the source of endless frustration. The DPA distributor-type fuel pump, sourced from CAV and supposedly proven in other applications, proved chronically unreliable when adapted to the V8.510's specific requirements. Later production engines used the Minimec pump system, but this change brought its own set of problems rather than solutions. Mechanics across Britain began reporting a consistent pattern of fuel system nightmares. The injection timing would drift without warning, causing rough running and black smoke. Speed regulation became erratic, with engines that would suddenly lock into single-speed operation regardless of throttle input. The adjustment procedures were so complex and temperamental that many service departments simply gave up trying to fine-tune the systems, instead replacing entire fuel pumps whenever problems arose. The problems weren't limited to urban bus applications. Long-haul truckers began reporting fuel system failures that left them stranded on motorways, often requiring expensive recovery services and emergency repairs at unfamiliar garages. The complexity of the fuel system meant that many independent mechanics couldn't properly diagnose problems, leading to misguided repairs that sometimes made the situation worse. But Perkins had decades of diesel experience and some of the best engineers in Britain. So how did they miss such fundamental flaws during development? What was really happening behind closed doors at their Peterborough headquarters? The answer involves a revelation about their testing procedures that only came to light years later when internal company documents were leaked during a legal dispute. Perkins had indeed conducted extensive dynamometer testing, logging thousands of hours of operation under controlled laboratory conditions. The engine had performed flawlessly on the test bench, meeting or exceeding every design specification. Power output was consistent, fuel consumption matched projections, and reliability seemed excellent. However, the real-world field testing program tells a completely different story. Under intense pressure from senior management to launch the engine ahead of competing American designs, the field trial program was drastically shortened. Instead of the recommended 18-month validation period involving dozens of engines in various applications, the actual field testing lasted just 6 months and involved fewer than 20 engines, most of which operated in relatively moderate conditions. Even more damaging, the feedback from the limited field trials was largely ignored when it conflicted with the laboratory results. Several trial operators reported fuel system inconsistencies and vibration problems, but these were dismissed by the engineering team as operator error or maintenance issues rather than fundamental design flaws. The commercial pressure to launch the engine was simply too great to allow for proper investigation of these early warning signs. This decision to rush the V8.510 to market would prove to be one of the most costly mistakes in British automotive history. Essentially, paying customers became unwitting beta testers for an engine that should never have left the development phase. The consequences of this decision would reverberate through the industry for decades. Generator applications presented their own unique nightmare scenario. Operators who had invested heavily in V8.510 powered emergency generators discovered that the fuel system's erratic behavior made precise speed control virtually impossible. For electrical generation, maintaining exact RPM is critical because frequency stability directly affects the quality of power output. Variations in engine speed translate to variations in electrical frequency, which can damage sensitive electronic equipment. Data centers, telecommunications facilities, and other critical infrastructure installations that had specified V8.510 generators found themselves facing potential catastrophic failures during power outages. The very applications where reliability was most critical became the engine's greatest weaknesses. Then came the overheating crisis, a problem so severe and widespread that it effectively ended the V8.510's commercial viability. Despite Perkins' confident claims about their advanced cooling system design, operators began reporting catastrophic failures involving complete cylinder bank overheating. These weren't random occurrences, they followed a disturbingly predictable pattern that suggested fundamental design flaws rather than isolated manufacturing defects. The overheating invariably affected one cylinder bank more severely than the other, creating a cascade of problems that would ultimately destroy the entire engine. The process typically began with slightly elevated temperatures on cylinders 2, 4, 6, and 8. As mineral deposits accumulated in the cooling passages serving these cylinders, the temperature differential increased. Higher temperatures led to more rapid mineral deposition, creating a positive feedback loop that quickly spiraled out of control. The symptoms were unmistakable. Operators would first notice steam or white vapor emanating from one side of the engine compartment. Temperature gauges, if properly calibrated and positioned, would show dangerously high readings for the affected bank. Within hours or sometimes minutes, head gasket failure would occur, allowing coolant to contaminate the combustion chambers and oil systems simultaneously. The root cause was a fundamental miscalculation in the cooling system's hydraulic design. While the centrifugal water pump could move adequate coolant volume, the internal passages weren't properly balanced to ensure equal flow distribution between the two cylinder banks. The passages serving one bank were slightly more restrictive, creating lower flow rates that became critical under high load conditions. Making matters worse, the dry liner construction that had been promoted as a maintenance advantage actually contributed to the cooling problems. The thermal expansion characteristics of the dry liners didn't perfectly match the aluminum block material, creating microscopic gaps that disrupted heat transfer. Under sustained high-load operation, these gaps would widen, further reducing cooling efficiency in the already compromised cylinder bank. Australian operators, who had initially been among the most enthusiastic adopters of the V8.510, quickly became its harshest critics. The combination of extreme ambient temperatures, long operating distances, and limited service infrastructure made cooling system failures particularly catastrophic. A single engine failure in the remote Australian interior could cost thousands of pounds in recovery expenses alone, not counting the lost cargo and schedule disruption. Major Australian transport companies began implementing formal policies prohibiting the purchase or lease of any vehicle powered by Perkins V8 engines. The Australian Road Transport Association published technical bulletins warning members about the cooling system problems and recommending alternative engine choices. Within 2 years, the V8.510 had become virtually unsellable in one of its most promising markets. The lubrication system presented its own catalog of problems that seemed to multiply rather than diminish with accumulated experience. While the gear-driven oil pump was theoretically robust and had proven reliable in other Perkins applications, the splash lubrication system for cylinder bores and gudgeon pins proved entirely inadequate under the sustained high-load operation that the V8.510 was designed to handle. Ring wear accelerated at alarming rates, particularly in applications involving sustained highway speeds or continuous industrial operation. The problem wasn't simply a matter of inadequate lubrication volume. The splash system couldn't reliably deliver oil to all critical surfaces under the dynamic conditions created by the V8's firing sequence and vibration characteristics. Bearing failures became commonplace in applications that should have been well within the engine's design parameters. The main bearings, connecting rod bearings, and camshaft bearings all showed premature wear patterns that suggested lubrication starvation during critical operating phases. Even engines that received meticulous maintenance and premium lubricants would develop bearing knock within 50,000 miles of operation, a fraction of the expected service life. The precision machining that had been showcased during the engine's launch became a liability rather than an advantage. The tight tolerances that contributed to the engine's impressive power output also made it extremely sensitive to any reduction in lubrication effectiveness. While a more robust engine might tolerate marginal lubrication for extended periods, the V8.510 would suffer immediate and often irreversible damage. Service complexity compounded every single problem and created new ones that hadn't been anticipated during the design phase. The compact packaging that looked so attractive in marketing brochures became a technician's worst nightmare when actual maintenance was required. The outside-mounted injectors, which allowed for easier manufacturing and assembly, required longer fuel lines that were prone to air leaks and pressure losses. Accessing routine maintenance points like oil filters, fuel filters, and coolant drain plugs required partial disassembly of surrounding components. What should have been a 30-minute service interval became a multi-hour ordeal that tested the patience of even the most dedicated mechanics. The cramped layout also made proper diagnostic procedures nearly impossible, forcing technicians to rely on guesswork rather than systematic analysis. The warranty claims began arriving at Perkins headquarters within 6 months of the engine entering full production. Initially, the company attempted to address problems through technical service bulletins and revised maintenance procedures. Field service representatives were dispatched to major customers to provide additional training and support. But the problems were too fundamental and too widespread to be resolved through improved maintenance practices. By 1967, warranty claims were arriving at a rate of nearly 100 per month, each representing not just the cost of engine replacement, but also consequential damages. Stranded cargo, missed schedules, passenger delays, and equipment downtime created legal liabilities that far exceeded the original engine purchase prices. The legal department at Perkins found itself managing hundreds of individual cases across dozens of countries. Fleet managers who had initially embraced the V8.510 as a technological breakthrough began implementing formal procurement policies specifically excluding Perkins V8 engines from consideration. London Transport, one of the world's largest bus operators, issued a company-wide directive banning the purchase of any vehicle powered by Perkins V8 engines. Similar policies were adopted by major operators across Britain and the Commonwealth. The commercial reputation damage extended far beyond the V8.510 itself. Fleet managers began questioning the reliability of other Perkins products, even the well-established inline engines that had built the company's reputation. The association with the V8.510 debacle tainted the entire Perkins brand in many markets, particularly among large fleet operators who couldn't afford the risk of similar problems with other engine models. Media coverage of the problems was extensive and generally unsympathetic. Trade publications that had initially praised the V8.510's innovative design began publishing detailed accounts of field failures and customer complaints. The British automotive press, already sensitive about the country's declining competitiveness in global markets, treated the V8.510 problems as symptomatic of broader issues with British engineering and quality control. International coverage was often even more damaging. American trade publications used the V8.510 failures as evidence that British manufacturers couldn't compete in sophisticated markets. Australian media coverage was particularly harsh, given the severe problems experienced in that market's demanding operating conditions. The global perception of British diesel technology suffered lasting damage that extended far beyond Perkins itself. By 1970, the situation had become untenable from both financial and reputational perspectives. Major component suppliers began refusing to provide parts specifically for V8.510 applications, citing concerns about liability exposure. Insurance companies started excluding V8.510 powered vehicles from standard coverage or requiring substantial premium increases to account for increased claim risks. And here's the twist that sealed its fate. It came from an unexpected technological development that caught the entire industry off guard. Turbocharging technology, which had been a specialized solution for marine and industrial applications, suddenly became practical for commercial vehicle engines. Turbocharged inline-six engines could now achieve power outputs that matched or exceeded the V8.510 while offering dramatically superior reliability, fuel economy, and service simplicity. Caterpillar's introduction of their turbocharged 3406 series in 1973 effectively made naturally aspirated V8 diesels obsolete overnight. The new turbocharged engines offered 250 horsepower or more from inline-six configurations that were lighter, more compact, and infinitely more reliable than the troublesome V8.510. The turbocharger revolution transformed the entire industry and rendered Perkins's investment in V8 technology worthless. Perkins made several desperate attempts to salvage the V8.510 program through extensive redesign efforts. They completely revised the fuel system, incorporating lessons learned from the field failures. The cooling system was redesigned with larger passages and improved flow distribution. The lubrication system received upgraded pumps and revised oil delivery circuits. But these improvements came too late to save the engine's commercial reputation. Fleet operators who had been burned by the original V8.510 problems were unwilling to risk their operations on revised versions, regardless of the improvements. The few customers who agreed to trial the improved engines did so only with extensive warranty protections and penalty clauses that made the business uneconomical for Perkins. Production of the V8.510 officially ceased in 1974, though Perkins continued providing parts support for existing engines until the early 1980s. The total production run was estimated at approximately 14,500 units, a small fraction of the 100,000-plus engines that had been projected during the optimistic planning phase. Most of these engines were scrapped or replaced within a few years of manufacture, making surviving examples extremely rare today. The financial cost of the V8.510 program was never fully disclosed, but industry estimates suggested total losses exceeding £50 million in the 1970s currency, equivalent to hundreds of millions in today's money. This figure included not just development costs and manufacturing losses, but also warranty claims, legal settlements, and the immeasurable cost of damaged reputation. The engineering lessons learned from the V8.510 debacle weren't entirely wasted, however. Perkins's subsequent engine development programs incorporated dramatically more rigorous testing protocols and conservative design margins. The company's engineers became almost obsessively careful about real-world validation, conducting extensive field trials lasting years rather than months before any new engine reached production. Modern diesel technology has long since surpassed everything the V8.510 promised to deliver, but the engine's influence can still be seen in contemporary designs. Direct injection has become universal. Electronic controls have eliminated the fuel system problems that plagued the mechanical systems, and advanced materials have solved the cooling and lubrication challenges that destroyed so many V8.510s. Perhaps most importantly, the V8.510's legacy lives on in the development methodologies used throughout the industry today. The comprehensive testing protocols, extensive field validation programs, and conservative design margins that characterize modern engine development all trace their origins, at least in part, to lessons learned from failures like the V8.510. So, have you ever encountered one of these rare engines in person, perhaps in an old generator set or vintage truck? Share your answers in the comments below. And if you enjoyed this deep dive into diesel engineering history, make sure to hit that subscribe button for more stories about ambitious projects that change the automotive industry. Until next time.